Problem formulation in modeling, a summary. This video is part of a course on food physics, of which this belongs to the modeling section. This is the last one in a series of 7 videos, and the other videos were getting into details of the problem formulation step. This one simply summarizes those steps. And here are those steps in problem formulation. At the end of these steps, we get a set of equations that represent a physical process and thereby replace the physical process. So all these steps that you see here, 1, 2, 3, 4, 5, 6, these are also individual videos in this series that discuss the details of the steps. So if we go through each one, first we have to set goals in a way that we can compute. To say that I want to compute quality or safety is not enough. We have to define those in quantitative terms. Then we simplify geometry. Then we choose a framework for modeling the physics amongst the many possibilities, from very simple to very complex. And even within the framework, then we have to simplify the equations to keep only the relevant physics. After this, we choose the most realistic boundary condition that represent the process. Then we choose the most realistic, material properties and parameters that are good enough to get started with the modeling process. They may not be the most accurate, but they're good enough to get started. So after this, we have a set of equations, and these equations together with the values for the parameters or the properties, they replace the original physical problem. All these steps in problem formulation here that convert a real physical process into its mathematical equivalent introduces errors due to approximation of the physical reality. We cannot solve the physical reality exactly, but also it introduces uncertainties. And we can think of two sources of uncertainties. One is the natural biological variability, like the potato material is going to vary in its property from one lot to the other, but also for a complex material process combinations as food is, we have unknowns. What we think of as the physics going on may not be completely correct, and we don't even know about it. So there are these unknown unknowns that also add to the uncertainty in our formulated model. Now the next step after we form this mathematical model, that is the equations, governing equations and boundary conditions, of course we solve them either using a software or writing our own code. But the point is, even if we have a way to solve these equations exactly, the errors and uncertainties that we have already made in the mathematical model, they do not go away. They stay with our final answer. They stay with the simulated results. So this is why we need to be really mindful of the decisions that we make in the problem formulation stage. This is why this step is very critical. While reducing errors and uncertainties call for more details to be included in the model to make it closer to reality, and we can always think, what the heck, we have very good software these days and we have lots of computing power, so why not include more of the details to make it more realistic. We still need to be concerned about computing time and effort. And we can easily make a model too complex to solve or debug. This is why we still have to simplify as much as possible. However, we need to be careful that we do not throw out any critical physics. That's what is meant by the word no simpler. So we have to continually balance between simplifying and on the one hand, on the other hand, making sure we are not throwing away some critical physics. Our golden rule is to start from the simplest and build in the complexities one at a time. In that process, here are few items that are worth considering. First, of course, we should know the physics that we are about to model. We should know enough of it. For example, in microwave heating, we should not get into microwave heating just because we have access to a solver for Maxwell's equations. We need to learn about microwave heating enough before we get into modeling a microwave heating process. Then goal. A goal must be quantitatively defined. So it's not enough to say we want good quality. We want to define what is good quality that is computable. Another one, we may have good software to handle a 3D problem, but that's not the reason to get into a 3D geometry initially. We should try the 2D first. Another one is we should start from constant properties, constant values of boundary conditions, and so on before we bring in time varying or spatially varying information. As we formulate the equations, we really obviously should keep in mind the capabilities of the software that we'll use to solve those equations. Otherwise, we'll be stuck in how to solve the equations that we have formulated. And then finally, every model needs to be validated and typically experimental against experimental data. It is useful at this stage to consider what experimental data do I have access to or I will be able to collect myself to make sure that we're computing the right quantities that we can validate against the experiment. Otherwise, we'll be stuck at the validation stage where either we have to do new experiments or we have to change our model. You may now want to pause the video and make sure you have applied the various steps that we have been talking about to your project, and we had similar pauses in the previous videos of this series for each one of these steps, giving you time to do that. Now is the time to put all of those together. So let's go through those steps quickly. We need to make sure that we have goals in quantitative terms. That's like step one. And then we need a schematic or a computational domain. That's the geometry over which you're going to do the computation. But before the geometry, for the sake of your own understanding or your group's understanding, we should also have a picture or cartoon of the real world. So these two, if they're put side by side, that is very helpful. And then we need the dimensions, each of the dimensions in the geometry that you have in step 2. So that's also another critical step. You want to make sure before we start the modeling process. Then you want to make sure you have all the governing equation, boundary conditions, initial conditions, and it would be nice to include, if possible, these equations or their word descriptions on the schematic in page 2 or step 2, I mean. On step 2, when you have this schematic, we should write on the schematic, include these physics. And the goal of all this is to communicate within the group or eventually to the outside world or to the people this modeling was intended. It's very important to build these pieces as we go along. Then we have the best estimate of the properties. So we have some properties in hand, may not be the very best or ultimate most accurate properties, but we have something to get started, but we also have some idea of their variability. And then this step, which was not included in the past, so this 4, 5, and then this is a step that we haven't discussed in the past. That is, before we get to actually solve the equations, we should have qualitative understanding of the process. And so we should have some idea of the expected results. This is kind of critically important. So let's look at this in little more details. We should have a reasonable idea of the physics and what to expect from the solution. We should not be waiting for the software to kind of surprise us. That is, we should have a qualitative picture in mind before we get started with solving. Especially at the early stages, the results are often wrong. And so we should be able to judge based on our understanding of the physics whether we're moving in the right direction or not. Once we are done with these steps, we have completed the problem formulation step of a modeling process, at least for now. Why for now? Because it is necessarily an iterative process. We learn from trying to solve the equations, trying to compare with experimental results, that we may need to come back and tweak the model, tweak the problem formulation. So it is an iterative step, but for now we are ready to solve the equations. So we are here. We are trying to implement. The next step would be trying to implement the model typically in a software or write your own code. Like the problem formulation step that we just completed, this one, we had where we had a series of videos. Likewise, the implementation of the model, and then the validation, and then the communication aspects, they all have their series of videos. The very next step, that is this implementation step, has to do with learning a software and then solving the equations that we got from the problem formulation step using this software. And so for this, we have a set of videos on this implementation on how to get started on one of the software. This one happens to be for the software COMSOL. So we have a set of videos on how to get started with implementing a formulated model in the software for solving the equations that we got out of problem formulation.